So we're going to focus on what role probability plays in inductive arguments, in assessing inductive force. And perhaps that overlaps somewhat with what we talked about so far already. So let's see how that goes. So to make it more specific, and this graph is given in the book as well, what we're interested in is, you could call the conditional probability of the conclusion given that the premises are true. So given all the premises, how probable is the conclusion to be true? And if it's more likely to be true than not, then we say that the argument is forceful. That's why starting just above 0.5, as indicated in the excellent question, the forceful argument starts. So given what we're gauging here is the conditional probability of the conclusion given the premises. If that probability is 0.5 or lower, we're saying that the argument is not forceful. If it's higher but below 1, then you can say it's forceful. And if you know that the probability of the conclusion given the premises is exactly 1, you call the argument valid. What I'm trying to show you is how we can use probability for thinking about, mainly inductive force. And you should realize that both validity and force are properties of the argument as a whole, right? So that's that first step in that critical thinker's two-step. They're not properties of individual propositions. So you can't say that's a forceful proposition, or that's a forceful conclusion, or you could say that's a forceful argument. So the implication of the premises for the conclusions are strong. And you can't say that a forceful argument is at least half true, or a conclusion in a forceful argument is at least half true. No, you can say that you're either judge that conclusion to be more likely to be true than not, you judge that conclusion to be more likely to be true than not, or you're not convinced in that way. The conclusion itself is in actuality either true or not. It's not half true or not. It's just, we're not talking about whether it's actually true, but we're talking about the degree to which we should be convinced about its truth, given that the premises are true. Okay. So we can talk about our degree of belief that the conclusion is true in different ways, or we can talk about probability in different ways, which we'll return a couple of times during the course. So it's important to be clear about that. So you can say that probability is about the state of the world, and then we're talking about objective probability, and that's the form of probability or the type of probability you're most familiar with, right? So it's an objective probability. We're talking about a frequency in which something might occur, right? So out of 80 out of 100 days it was sunny, so the probability of sun on similar days is 80%, or 0.80, and because the relative frequency of sunny days on similar days was 80 out of 100. Or if you draw a card, or flip a coin, or throw a die, that's all objective probabilities. What we're not talking about. P-values are objective probabilities as well. But there's a different type of talking about probabilities which entails something else, which is called subjective probability, and that's not about the world itself. That's not the state of the world, the frequencies or the proportions in the world. It's about your beliefs about that state of the world. So the degree to which you believe something to be true. And that's the type of probability we're actually talking about when we're talking about the degree of rational expectation. The degree of rational expectation is the degree to which you should expect a conclusion to be true, given that the premises are true. So given these assumptions, your rational degree of belief about the conclusion should be that it's more likely to be true or not, or sometimes you can give it a more specific percentage. And sometimes it's difficult to imagine that you can give a more specific percentage or to your degree of belief about the state of the world, right? So a thought experiment could be, if I give you the following options. So you're at the exam and I'm standing next to your table, right? This is pre or post corona. And I'm asking you, so open the next question, and you're reading the next question. And I say, well, okay, you have two options. You can either answer the question and see how it goes, right? You either have it correct or not, and you get a point or not. You get a point if it's correct and no point if it's incorrect. You know how it goes with exam questions. Or you could not answer the question, and I flip a coin, and if it lands head, you get a point. And you can choose between the two, right? So if you're more inclined, given the content of the question, to go for the Toynbee, then your degree of belief about your knowledge about this question being correct would be lower than 50% in this case. At least that would be the rational inference from this situation. So in this way, with these type of choices, would you either go for the result of a Toynbee or your knowledge about this question, or would you rather have... there's different examples that I could give, but in this way, you're at least trying to pinpoint a certain number to your degree of belief. In this case, the degree of belief that you have the correct answer, the correct knowledge. Do you think that's below or above the 50% chance that you would have if I would flip a coin? So then we're assigning a number, or at least getting to a number, and trying to assign that to your degree of belief that something is the case. In any case, we can talk about probability in two ways: subjective and objective probabilities. Subjective probability is informed, of course, by objective probability. So if you throw some dice and you ask, what is the probability? To what degree do you believe that the die you will roll 6, for example? Then of course you're going to say 1 out of 6, and in that case your subjective probability, your belief about the world, is in line with those objective probabilities as well. We're taking a more general approach, or the book is taking a more general approach, and we're bunching these together. However, wherever you get them, the probabilities, be they subjective or objective, we can talk about the degree of rational expectation. So whatever the probability, subjective or objective, given in the premises, if we assume them to be true, would it be rational to believe the conclusion to be true or not? So we're again talking about those connections, and we're talking about the degree of rational expectation. All right. So let's look at what that means, because we can use the rules of probability so we need to use those rules for probability to figuring out whether it's rational to believe the conclusion to be, or to expect the conclusion to be true or not, right? That's in line with the benchmarks we talked about last week. When I said it's rational to update your belief in accordance with the rules of probability, that's what we're talking about here. Is it rational to believe the conclusion to be true, given that the probabilities in the premises are true? So let's see what that means, because it's a bit abstract, and we're going to make it more concrete. So if I would say, on most days I eat bananas, I probably spray whipped cream in my mouth when I eat a banana. Can I then, with some force, conclude that I spray whipped cream in my mouth? Is the conclusion probably true, given that the premises are true or not? Is this a forceful argument or not? No. Why not? Yeah, because you use probably in both premises. Very good, Eva. Thanks. There's a probably in both premises. So exactly, Bram. That's a good calculation. So what I'm saying is that on most days, so more often than 50% of days, I'm eating bananas, and in 50% of those days, I do the whipped cream thing. So that, at the very least, gives us a 25% chance that the conclusion is true. But that's below that threshold that we talked about. So you would call this a not forceful argument. So it's not valid and it's not forceful. This is an example of how you can use probability when trying to assess inductive arguments. Another example is when I go to the lecture, I'll probably glance at my book. When I glance at my book, I'll probably critically read the correct passages. So can you therefore conclude, when I go to the lecture, I'll critically read the correct passages? Again, indeed, Gabriella, the same. It's the same type of argument, but I replaced the whipped cream and bananas with something you're hopefully more familiar with. We can't say this argument is forceful because the conditional probability of the conclusion being true, given that the premises are true, is below that 50% threshold that we talked about.
Something?
Yeah, sure, go ahead.
So if the conclusion would be, when I go to the lecture, I'll probably critically read the correct passages, that would be forceful?
Yeah.
Okay.
Yeah. Indeed.
Okay, thanks.
But usually I won't make things that complicated in actual exam, so don't worry about it. Okay, so if we take this argument, and one way of analyzing this argument is using these tree diagrams that we used with deductive arguments as well, right? You don't need to use them, but you could use them if you're confused by the probabilities. So what I've depicted here, that when I go to the lecture, in 50% of cases, I'll glance at my book, and in 50% of cases, when I glance at my book, I will do some critical reading. And that way you can better understand why just in some of all possible situations the conclusion will be true, but not necessarily in all cases. There's one way of using those probabilities. And we'll return to that tree diagram with a different example when we're talking about calculating conditional probabilities in a while. Another way of making this more intuitive is checking out, I go to the lecture, and in half of the cases when I go to the lecture, this is the box of all situations in which you go to the lecture, and you can say that at least half of those situations contain situations in which you glance at a book. And again, the second premise adds that in at least half of the situations in which you glance at a book, you actually read the book in a critical way. So if we then check the conclusion, does that necessarily mean, or probably mean, that you critically read the book when you go to the lecture? No. That's just at least 25% of the cases. When you go to the lecture, you're actually critically reading the book. Hopefully that helps. At least it helps for me, this type of illustration, to make it more intuitive why that conclusion doesn't necessarily, or doesn't even probably hold, given the premises we just discussed. All right, let's move to a different type of task, which has to do with conditional probability more specifically. So let's say, given are the following three premises: 9 out of 10 SSR students are vegetarians. Only 1 in 10 non-SSR students are vegetarians. Bobette is a vegetarian, so that means Bobette is an SSR student. Is this a valid argument? Is it a forceful argument? What do you think? Is it neither? It's invalid. Okay. Neither, says Lucy. Neither. I saw some invalids, I saw some forcefuls, and I saw a couple of neithers. All right. Zoe, could you illustrate your answer?
It is invalid because there's the premises don't logically conclude that Bobette is an SSR student. Mm-hmm. It is unsound because, let's have a look. You should let know in the conclusion that it is probably, I think. So if you say in the conclusion, Bobette is probably an SSR student, then it is sound because it is a true statement. And because the premises are now not completely true towards the conclusion, it's forceful. And not sound. All
right, yeah, I think that's a very good crack at the answer, but I do have the impression that you confused two of the terms that we've been using. So I think I agree with you. It's not valid. So the conclusion is not guaranteed to be true, given that the premises are true. Soundness is about whether the premises are in fact true. Right? So whether Bobette is actually a vegetarian, or whether it's actually true that only 1 in 10 non-SSR students are vegetarians, I don't know whether that's true or not. But that's what you check with soundness, right? That's a final step. So before you check soundness, so you start indeed with checking validity, then you move on to checking for inductive force. And only if you consider it to be forceful, you would check for soundness as well, which is about...
You can say that it's forceful because they it's actually a probability answer, but they say that it's the case.
Yeah, but you could also, but regardless of whether people use the word probability or probably in the conclusion, you can check whether that conclusion, that Bobette is an SSR student, is more likely to be true or not, given the premises. So it's good you point that out, because I want to stress that even though the conclusion just said this is the case, you can still check whether that statement of that being the case, Bobette being an SSR student, is more likely to be true or not, given that the premises are true. So you can check for inductive force. But the yeah, go ahead.
But you can, like, if only 1 in 10 non-SSR students are vegetarians, you can, the chances are bigger that she is an SSR student than that she's not.
So
It's forceful.
All right. It's not forceful, but it's good that we got those terms clear, right? So we checked validity, which you did, and you did properly, and then you checked for forcefulness, and you thought, well, it's forceful because of that second premise. And that's actually not correct, but that's a mistake that a lot of people make. So that's a very common error in reasoning about probabilities, which is called the base rate error. And that has to do with the fact that base rate actually isn't given here, and we need it for properly calculating the conditional probabilities. Let me show you what I mean by that, and why both invalid and not forceful would have been the most correct answer here. Thank you for your input, Zoe. Awesome that you wanted to illustrate your answer. Thanks. So we want to know whether what we need to know for judging whether the conclusion is more likely to be true or not given the premises. What we want to know is what the probabilities of that conclusion given the premises. So we need to know what the probability is of somebody being an SSR student given that they are a vegetarian. And we need to figure out whether we can calculate that probability using the information in the first premises. So let's have a look. So we could symbolize the premises here. So you could symbolize the statement 9 out of 10 SSR students are vegetarians by saying the probability of being a vegetarian given that you're an SSR student is 90%. You can symbolize the second statement by saying the probability of being a vegetarian given that you're not an SSR student is 10%. And then you're saying Bobette is a vegetarian. There's no symbolizing that. And then you're concluding Bobette is an SSR student. So what we need to know is the probability of being an SSR student using those same symbols given that somebody is a vegetarian. And that should be more explicit once you look at it in these using these symbols. Is that the symbol that the probability that we need is the reverse of the probabilities that are given in the first two premises, right? This says veggie given SSR, veggie given not SSR, and this says SSR given veggie. So we need the inverse of the probabilities that are given here. So you can't just take over those probabilities, but you have to do something with them. And perhaps as you remember, you need actually three types of things, right? So what we need to calculate is the probability of SSR given veggie. What we have is veggie given SSR and veggie given not SSR. And if we then look at the formula for calculating conditional probabilities, then we know what we actually need. And I've used colors to indicate what we have from this formula, and you should see that the red thing is absent. So what we have is, what we need to know is the probability of SSR given veggie. So I've colored the first part of the formula for conditional probabilities, colored that yellow, because that's the one thing we want to know. And what we need for calculating that is the inverse, depicted in green, and the inverse is given in the problem, right? That's the probability of veggie given SSR. That's the inverse of that. Right, what we also need is the base rate. So the probability of a student or a person being enrolled in SSR without any conditions. So the unconditional probability of somebody doing the course SSR, which presumably is very low. And that's absent from the formula. So if you wanted to calculate the probability of somebody taking SSR given that he or she is a vegetarian, what you would need besides the stuff we already have is the base rate as well, before we can say something about inductive force. That's why it's called the base rate error, right? Because people encounter an argument which lacks information about the base rate, but they still think it's a good argument. Because they neglect the fact that they need the base rate for making calculations about probabilities, conditional probabilities. All right, so what we've looked at is an inductive argument, and we need a conditional probability for figuring out whether the conclusion is more likely to be true or not, given that the premises are true. But it's highly that probability that we need for that conclusion is highly dependent on the base rate, which isn't given here, and it's not unimaginable that the a priori or the base rate, a priori probability or the base rate of being a SSR student, given that you're a human being, isn't very high, right? So even if we don't know the base rate, presumably is very low. But the point here is not necessarily that we can imagine it to be low or high, but that it's not given. So we can't strictly say that this is a forceful argument.